Hi there, today I want to take a look at the determinant of a 2 by 2 matrix here and the area of a parallelogram formed by vectors comprising of this matrix. So what am I talking about? Well, here's a 2 by 2 matrix here, A, B, C, D. If vector 1 is AC, that's this part here, and vector 2 is BD, that's this vector here, and I plotted them on a little diagram, I can see vector 1, vector 2, and if I joined up the following lines, I can get them to form a parallelogram. Okay, so that's pretty cool. Now, what we've been told is that if I work out the determinant of this matrix, which we know is AD minus BC, now we've been told that'll give us the area of this parallelogram. So today I want to take a quick look at that and see whether or not that is the case. So let's start. Now I've sketched my parallelogram here for my two vectors, vector 1 and vector 2. And what do we need? What's the formula for the area of a parallelogram? Well, it's simply the base there times the perpendicular height. So that's quite nice. I've written that up there. And what do we have? Well, we have the base. That's quite easy. That's just the magnitude of vector 1. But what about this value here? The height, or the perpendicular height of the parallelogram. Well, I don't have that, but I can kind of find it because I've got the magnitude. I've got a right angle triangle here. The hypotenuse is the magnitude of vector 2, and this part here, this little length I've called R, is the projection of vector 2 onto vector 1. So if I can find the length of that, we can, do a bit of a Pythagoras and find the length of H. Okay, so that'll help us enormously in finding the area of this parallelogram, which should equal the determinant. Okay, so let's continue. So I've said there area equals base times height, and then I've just squared both sides. This is going to make it a bit easier as we work through the quite a lot of working to do. So a squared equals b squared plus h squared. Nice and easy. Yep, so you've got b squared, and that's the magnitude of vector 1 here, and just squared because it's b squared. Okay. So that's all right, and from previous work on vectors, we know that it's just the length squared is simply the vector dotted with itself. Okay. Okay, then the next bit we can look at is this part containing R. Now I know, with here it is here, I've written down h squared, the height squared. Well, that's going to be the hypotenuse squared minus this side squared, and the hypotenuse squared is the magnitude of vector 2 squared, and that's going to be minus r squared. So what is r squared? It's the projection of vector 2 onto vector 1. Now down here there's a little formula we can use for that, and it's v2 dot v1 divided by v1 dotted with itself. Now remember, this just gives us a scalar or a number, and this gives us a scalar or a number. And what this will give us is the proportion, the amount of vector 1 that R takes up. Okay, so look, this will be some fraction of vector 1. Okay, and this will go into here. So let's do that. So just like vector 1, the length of vector 1 squared, or the magnitude of vector 1 squared, is the same as v1 dotted with itself. The magnitude of vector 2 squared is v2 dotted with itself. So I can replace that with this. And r squared is just this gubbins up here, substituted in there and squared. So that's quite straightforward. Now what I'm going to do is just square out these brackets. I'm just going to multiply this by itself. So I get all that here multiplied by itself again, and vector v1 I should really say dotted with itself. And vector v1 dotted with itself there. And so it's just multiplying out this squared term in the brackets. Now I can see there them v1s cancel. These two terms cancel. So I can come down and write that again. And these two terms square. So we end up with this situation. Now the next step I can do, I've got my b squared here and my h squared here. Now let's write them together. So this part goes down to there and all this is in here. Okay, I've written them down together. So this is a squared equals b squared h squared. Now you can see I could multiply through the brackets by this term here, v1 dotted with itself. And when I do that, this term will cancel out with that term, right? So you end up with a squared equals this times this minus this lot. Now what can I do next? I can substitute the actual values in. So what's v1 dotted with itself? Well, that's going to be a cubed, a squared plus c squared. Yeah, it's a bit like Pythagoras stuff coming in again. And v2 dotted with itself, yeah, we've got b times b plus d times d, or b squared plus d squared. That's exactly what I get there. So I'm just substituting in the actual values of the vectors here. And what's v2 dotted with v1? Well, it's going to be a times b plus c times d. And that's what I've got there, and that's a minus, and that's all squared. Now the next bit I can do FOIL on these brackets here, multiply them out or expand these brackets using FOIL, and then do the same for this one. Multiply this bracket by itself. And when I do that, I get this part becomes this long bit, and this bit becomes this bit here. You'll notice this bracket's going to multiply through the bracket, so I can cancel this term and that term, that term and that term. And if I've got to have this, I have 3 terms left, and if I write them down, I end up with that. So then what? That looks a little bit familiar, and it's if you swapped all those gubbins for like x squared minus 2xy plus y squared, you'd see you could do x minus y squared. In our case, the equivalent terms. So I've got a value or an expression for the area squared. Now if I take square roots of both sides, I end up with the area being equal to AD minus BC, and that is exactly the determinant of a 2 by 2 matrix. So that's quite the thing. We've just proven that the determinant of that 2 by 2 matrix will give us the area of this parallelogram. Absolutely lovely. Okay, thanks.